Dr. D here, and today we're going to learn a little about intermolecular forces. We are going to focus mainly on polarity, but we'll also discuss phases of matter, hydrogen bonding, dispersion, and ionic bonds. So let's dive into it in Content with Content. So to begin things off, I want to use a few molecules as an example for talking about intermolecular forces. And so our first one we're going to talk about is ethanol, with a molar mass of 46.07 grams per mole and a density of 789 kilograms per cubic meter. Now, one of the issues with drawing molecules is that we're trying to represent three-dimensional objects on a two-dimensional plane. So to start things off, I want to talk a little bit about how this is done. So if we look at this solid triangle here, this is a wedge. And what that means is that this molecule, or this hydrogen atom, is coming out of the screen, or coming out of the plane. And then we have another triangle with kind of spacing in between it, or dashes. And this is considered to be a dash. And this means that this hydrogen is going into the screen, or going into the plane. So to kind of represent this a little bit better, we have a picture of a model kit here. And I'm going to go ahead and put up some color-coordinated circles on here. So we have a red hydrogen coming out of the plane. We have our green hydrogen going into the plane. And then we have our blue hydrogen that's in the plane of the molecule just going up. All right. So the other molecule I want us to look at is propane, that has a molar mass of 44.1 grams per mole and a density of 2.01 kilograms per cubic meter. And if we were to make this with a model kit, it looks something like this. And then our last molecule I want us to look at is sodium fluoride, with a molar mass of 41.98 grams per mole and a density of 2,558 kilograms per cubic meter. Now for sodium fluoride, there aren't really model kits for ionic species, so we're going to settle for these circles that I drew. So looking at these three molecules, they actually experience different intermolecular forces, and this actually causes them to exist as different phases of matter at room temperature. So take a look at these, and they'll exist as a gas, liquid, and solid. So take a look at these and pause the video if you want and figure out which one of these you think is most likely a gas at room temperature. All right, so if you guessed propane, you'd be right. Now, some of y'all might have looked at the density and saw this was really, really low and figured out, all right, that's probably going to be a gas. Or you may recall that, on those nice summer days, you can go out there and grill up some burgers with some propane. All right. Now, one of the things that we could do to more justifiably say that this would be a gas is if we had some more information. So if we look at the melting point and boiling point, we'll see that it has a melting point of negative 188 degrees Celsius and a boiling point of negative 42 degrees Celsius. So since a room temperature, 20 degrees Celsius, is much higher than either of these, we would know that we would have to have a gas because it's greater than the boiling point. All right, so looking at our other two remaining molecules, which one of these do you think is a liquid? If you need to, take a moment, pause the video, and take a guess. All right, if you had guessed ethanol, you'd be right. So for ethanol, you may have recognized this one because it's the common ingredient in most alcoholic beverages. But if we have a little bit more information, we could look at the melting point being at negative 114 degrees Celsius and the boiling point being at 78.37 degrees Celsius. And so if we ever have our temperature, room temperature in this case at 20 degrees Celsius, if we have our temperature of our substance being between the melting point and the boiling point, we know that we have a liquid. All right, lastly, we have sodium fluoride, and that is going to be a solid. And sodium fluoride is commonly found in as an additive for toothpaste, and it's also added to a lot of drinking water. Not exactly thrilled about having halogens in my mouth, but It's kind of become a common practice these days. If we add a little bit more information here, we see that the melting point is at a whopping 993 degrees Celsius and a boiling point of 1,695 degrees Celsius. So this is crazy hot, much, much higher than 20 degrees Celsius. So if you ever have your temperature of your molecules being under the melting point, then you're going to have a solid. So these phases of matter actually happen due to intermolecular forces. So I want to go ahead and focus on ethanol to begin with, and we'll talk a little bit about what is causing this to occur. So if we look at ethanol, we'll see that we have mostly hydrogens, carbons, and oxygens. And so I want to pull up the periodic table, and we need to determine which one of these elements in this molecule is the most electronegative. So as a little refresher, the most electronegative element there is on the periodic table is fluorine. And so anything that's closer to fluorine is going to be more electronegative. And so when we're comparing hydrogen, carbon, and oxygen, oxygen is by far the closest one to fluorine, and it's going to be the most electronegative. So with this in mind, when we look at the surrounding elements to the oxygen, it's going to be pulling that electron density from them. So even though we have a covalent bond between this carbon and oxygen, it doesn't spend equal amounts of time with the carbon and oxygen. It's going to spend more time with the more electronegative species, oxygen in this case. And since the electron density is being pulled from this carbon is going to pull the electron density away from its neighbors, being the hydrogens, and even the neighboring carbon. And since this carbon is losing some of its electron density, it's going to pull even more of the electron density away from these other hydrogens. And then lastly, we have the hydrogen connected to the oxygen, and it's going to pull off most of the electron density away from that hydrogen. And what this does is this causes this oxygen to have a partial negative charge. And then we're going to have a partial positive charge at the other end of the molecule, where we have all the electron density being pulled away from. And so we can go ahead and draw a kind of special type of arrow. And at the tip of this arrow, this is going to be pointing towards the electron density. And then we're going to have a little plus sign at the other end of the arrow. And this means that this is located near the electron deficient end. And so if we ever have an uneven distribution of our electrons, or the electron density, this means that the molecule is going to be polar. So a lot of times, scientists will go ahead and draw this arrow either above or below the molecule to kind of help make things a little bit easier to see, and we get a general idea of where the electrons are going. And again, this will mean that if you ever see this, this means it's a polar molecule. All right. So we looked at ethanol, we determined it's polar. Let's go ahead and take a look at propane. So for propane, we see that we have only hydrogens and carbons this time. So when we look at our periodic table, we're trying to figure out which one's the most electronegative, and it looks like a no contest. It seems like hydrogen is on the complete other end of the periodic table compared to the fluorine, but this probably isn't the full picture. So one thing is to kind of keep in mind, if we're looking at electronegativity, hydrogen would probably be a little bit more likely to be just above carbon. Main reason for this is in order to get to a noble gas configuration, carbon has to either lose or gain 4 electrons. Similarly, hydrogen has to either lose or gain 1 electron. And so since they're both kind of split between the noble gas configurations, they actually have very similar electronegativities. So if you had to make a call between them, carbon just barely wins out, and so we'll have a very, very slight amount of electron density going towards the carbon, but to be honest, they're very, very similar. And so whenever you have just a molecule with just hydrogens and carbons in it, you don't have any double bonds or triple bonds, it is always going to be nonpolar, just meaning that it has an even distribution of electrons or electron density. The other thing to consider here is the shape of the molecule. So if we even went through and replaced all the hydrogens with, say, something like fluorine, which is very electronegative, it would still be a nonpolar molecule. So if we'll focus on the bottom left fluorines here, we'd see that the electrons to be pulled towards the fluorines from the carbon, and they'd be going in and out of the board, and that would actually cancel each other out because they're going in opposite directions. Now we'll also be seeing that they're going in a downward direction, but that would be canceled out by this other fluorine, where it's going to be pulling some electron density up. And so in a three-dimensional space, when we look at all the fluorines here, they're all going to cancel each other out. So this would be an overall nonpolar molecule, because we don't have any one side that is being favored with an excess amount of electron density. So going back to propane, we see that as a nonpolar molecule, and so we'll go ahead and add that to our list. Lastly, we got our sodium fluoride. So when we take a look at sodium fluoride, we'll see that we have sodium plus and fluorine minus. You'll notice that we have a plus and minus on here. This plus and minus is a charge. All right, and whenever we see a charge, that means that we have ions. So we have a sodium cation and a fluorine anion. And so whenever this occurs, we know that we have an ionic species, and that means we have a complete transfer of an electron. So that sodium is completely giving up its electron to the fluorine, and now they're going to have a charge. So this normally occurs whenever we have a metal interacting with a nonmetal. And this will always result in ionic bonding. And the reason that ionic bonding occurs is essentially due to Coulombic attraction. So going back to our list, we'll see that sodium fluoride is ionic. So we've determined that ethanol is polar, propane is nonpolar, and sodium fluoride is ionic, but we haven't really touched on why we have a liquid, gas, and solid. So to go into that a little bit, we need to talk about intermolecular forces, and this is the forces between two molecules. So let's take a look at our propane here, our ethanol here, and we know that it's going to be a polar molecule where the electron density is being pulled towards the oxygen, and then our carbon here is going to try to minimize its electron deficiency by pulling the electron density away from its neighbors, and so forth and so on. So we end up with a partial negative end on our oxygen, and a partial positive end at the end of the molecule, and a partial positive end at the hydrogen connected to the oxygen. And we know that this molecule is going to be polar. So there's actually two ways that this ethanol could interact with another ethanol. The first way, and probably the most predominant way, would be for the ethanol to essentially interact with the hydrogen and oxygen of another ethanol. So for the hydrogen and oxygen of the other ethanol, we're going to have a partial positive and partial negative end, and the hydrogen that is connected to the oxygen of each of those is going to interact with the other's oxygen. And so we're going to have some intermolecular forces going on here, and this is known as hydrogen bonding. Hydrogen bonding occurs whenever you have a nitrogen, oxygen, or fluorine with a hydrogen connected to it interacting with another nitrogen, oxygen, or fluorine with a hydrogen connected to it. And as I said, this is probably the more predominant way that ethanol would interact with another ethanol molecule. But another way it could interact is if we look at the molecule as a whole. We look over and we see that on the far right side, we have a partial negative end, and on the far left side, we have an electron deficient end. And so that could interact with the other partial positive end, and we'd have an interaction that's kind of considered a head-to-tail interaction. And this is very common for polar molecules, and this would probably have some characteristics or some contributions to ethanol's physical traits. All right, but with either one of these interactions are going to be fairly strong, and they're going to essentially hold on to the other molecules quite well, and so that's going to prevent them from going into, say, the gas phase. The gas phase being that there are no other interactions with that molecule. All right, so let's go ahead and look at our propane, which is a nonpolar molecule. So since we have a nonpolar molecule, it would interact with another propane, another nonpolar molecule, and there's not a lot of interaction that is going to occur here. We don't have one end that has higher electron density than the other, and so the only thing that's going to occur is we're going to have some what's called dispersion or van der Waals interactions. And I'll talk more about this in a later video, but basically the electrons will potentially go to one side, and that'll cause a partial charge on the other molecule, and so their electrons kind of alternate back and forth, going from, say, the left side to the right side. But for the most part, this isn't going to be as strong of an interaction, and so it's going to be a lot easier for these molecules to essentially be separated and go into the gas phase. So it results in a low boiling point. All right, and then looking at our last one, we have sodium fluoride, which is an ionic species. And for our sodium fluoride, when it's interacting with other sodium fluorides, since these are ions, this would actually form a kind of crystal lattice structure. So to help minimize the complexity here, I'm not drawing in 3 dimensions, we'll leave in 2 dimensions. But we'll have this very, very strong interaction between our original sodium fluoride and the other sodium fluorides. And so we're not only going to have to break this full-on ionic bond with this other fluorine here, but we're going to have to also break the intermolecular forces with these other sodiums as well. And so this type of interaction is called an ion-ion interaction. And keep in mind that this is essentially a full-on bond. It's ionic bonding still. And so this is very, very strong. In order to get that sodium fluoride to go off into the gaseous state, we're going to have to break a number of bonds for that to happen. And that's why it has such a high melting point and boiling point. So here's a list of the intermolecular forces with the strongest at top and weakest on bottom, where we have ion-ion, followed by ion-dipole, then hydrogen bonding, dipole-dipole, ion-induced dipole, dipole-induced dipole, and finally dispersion and van der Waals interactions. And for our 3 examples today, we had ion-ion, hydrogen bonding, and dispersion. So I'll be talking more about these in a later on video, but that's all I have for you today. So I hope you learned a lot and understand a little bit more about polarity. So as always, keep thinking, and I'll see you next time. Goodbye!